Okay, it's always great to be here at IPAM, and the work I'm going to talk about is joint work with Joel Leibowitz, who's my colleague at Rutgers, and David Hughes, who's a condensed matter physicist at Princeton University. So we're coming from an open systems point of view, which fits into the subject here. None of us are really algorithmic people, but I think there's actually been a lot of good contact, and so we'll see how this goes. I think I've been enjoying the talk so far, and let's see. Okay, so right, I won't be doing proofs per se, but all of the mathematical tools that I'm using in this system are described in this recent book that's appeared in the AMS Graduate Studies in Mathematics, and so this is the take on the background of it. So what the subject is, the collaborators here, will be considering a bipartite quantum system. So the Hilbert space is the tensor product of two Hilbert spaces. The red dots concern part A, and the teal dots are part B. And you should think of the A maybe as being part of the boundary, and the B being part of the bulk. I've arranged things in a line here, so it looks like a spin chain, and in the examples where you compute stuff, we're computing things in examples of spin chains, but the theory I'll be describing, there's no specific geometry associated to it. So there's just two parts of the system, but it's good to think of one of them as the edge, hence boundary-driven systems, and so forth, okay? So now, the evolution, of course, we have, we're looking at the CPT semigroup. So all of those in the finite-dimensional setting where we are have a Lindblad type generator. That's Lindblad's theorem, which gives the description of the general form of the generator of a CPT semigroup that's norm continuous. Okay, so everyone here knows, of course, what complete positivity is and why we require that. Okay, and the Lindbladian has two parts. There's a coherent part of the evolution and a dissipative part. To describe the coherent parts in our bipartite system, we'll assume that the Hamiltonian is traceless without loss of generality and split it up into these parts A, B. So the HA is just, you trace out the B and renormalize by the dimension, and that's the HA part, and this is the HB part, and then what's left over is the HAB, which is the interaction. And of course, we're interested in some real interaction between these things. Okay, so then this generator, which is the minus I times the commutator with H, so this superoperator is the generator of the coherent evolution. The dissipative part, as we know, has the Lindblad form, and I've written it without an additional Lamb shift thing here, but this is Lindblad's theorem, and this dA, okay, this thing is acting just on the A part of the system. So the red dots, so there's a dissipation. The Hamiltonian is acting on the whole system, mixing things up coherently, but these jump operators are operators on HA only, not HB, okay? And so that's what this is. We're assuming that the dA is ergodic, and it also has a spectral gap. So in this finite-dimensional setting, as long as the eigenspace for eigenvalue 0 is one-dimensional, and there are no purely imaginary eigenvalues, nothing periodic going on, then you'll have a spectral gap, and this just means that the real part of all the eigenvalues are less than or equal to minus A for some positive number A. Okay, so that's the gap. We're not assuming any kind of self-adjointness, so the eigenvalues can indeed be complex. Okay, so then the script D without the A on it is just the dA tensor, the identity. And the Lindblad equation we want to look at is this thing. So the full Lindbladian, L gamma, has the coherent part acting at unit speed, and there's this gamma in front of the dissipation, and the limit in which the coupling constant gamma goes to infinity is known as the Zeno limit in the physics literature. So this is sort of the Zeno paradox. The real Zeno effect was something first described or discussed by Alan Turing. There isn't a paper, but in 1954, in the last year he was alive, he observed that if you make an observation until you collapse state, and then it starts rotating out. So if you quickly look again, in a short time later, there's a time delta t squared probability that you get any other measurements. If you keep looking at things, it just stays fixed. Okay? Now, every sort of measurement comes from coupling to an environment, and so the D, this dissipation, you should think of it as the effect of some sort of observation. In any case, this is the terminology that's used. Okay? So it's going to keep things pinned in a way that we will describe here. Okay, good. So under the ergodicity hypothesis on this dA, so every density matrix that's in the null space of the script D, the dissipator part, has the form pi A tensor R for some arbitrary density matrix on HB. So that's the null space of the script D. And if you run this evolution forward, okay, it converges to this projector P, which is the limit of CPT maps is itself CPT. So it's a projector, not necessarily orthogonal. And what's going to be important for us is the rate at which this goes to 0. Okay? Now, this 1-1 norm is defined on the next slide. If you've got a super operator, you apply it to some operator x, and take the trace norm of that, and then take the sup over all things in the unit ball and the trace norm. And so this is the trace 1 to trace 1 super operator. This is the super operator trace norm. That's the relevant or the most natural norm for working with an evolution equation for density matrices. And it has many nice properties for us. We will make extensive use of the fact that any CPT map is a contraction in this norm, right? So, okay, good. Now, this, if you take the e to the d, this, we said earlier, this is e to the t dA tensor the identity. And this projector is the same thing as this rank 1 projector tensor the identity. So this map that we're looking at here is this thing tensor the identity. And using the spectral gap, it's easy to show that for some constant c, depending only on system A, you've got this exponential decay. The A over 2, you can, if you can diagonalize the D, you can throw away the 2, and you can replace the 2 with anything close. You can get as close to A as you want, but then the C gets bigger. For convenience, I'll just chop A in half, and we've got this. The important thing is this just depends on system A. This does not imply, if you tensor on the identity, this doesn't imply that this is going to decay at the same rate. Okay? So nonetheless, we can prove that this inequality holds with a constant that only depends on the dimension of A. In particular, it's independent of the dimension of B. Okay? So this is a mathematical question I would like to understand better. In addition to complete positivity, there's the notion of complete boundedness. So when you tensor on the identity for an arbitrary auxiliary Hilbert space and take the sup over all the dimensions of those, that's the completely bounded norm. And I don't know of a general theorem that says if you take two CPT maps and these are close to one another, and then you tensor on the identity, that you can, the thing with the identity tensored on is also close to 0. I'd like to be able to transfer this bound to this bound in some more generality, but okay?
It was only on this first level.
Right, right. So, okay, but fortunately, this dA is a small dimensional thing, and so I don't know if the sharp bound transfers, but we have a way of bounding this that does transfer to this, and so I can bound this independent of the constant C is independent of the dimension of the B space.
That's false, right? Because you have all these finite-dimensional operator spaces which are far apart, even though they're very close to together finite spaces. So.
Mm-hmm. Well, no, but this is okay. Well, you could do. So this decays. So you can transfer this one to this, okay, and this will come up important. So let M denote this set of density matrices that are of this form. So pi A tensor R, where R is anything, that's our local equilibrium manifold. And for large gamma, this dissipation term dominates, and so you should rapidly dissipate away so that to one of these near steady states and be pi A tensor something on B. Okay? So after a short time, and then you would expect to be evolving along with that. Okay? So this is indeed the case, and it was shown by Zanardi and Campos Venuti, okay, that for large gamma, this rho of t, that's the solution of the full equation, minus the projected version, okay, is of order 1 over gamma, uniformly in time for all t greater than an initial relaxation time, which is of order 1 over gamma. Okay, good. Now consider so we want to consider the solution of this Lindblad equation, and we're particularly interested in the long-time behavior and steady states. And so we'll define R of t by this projected version of the full evolution. And what we'd like to ask is how does R of t evolve, and what can we say about the limit as t goes to infinity of R of t? Okay, so since this p of R of t, by definition is this, we'd like to get an evolution equation for the R of t. Okay, so what can we say? So to describe this, I need a few more characters, but not many. So there's the complementary projection, q equals 1 minus p. And then if you project out the steady state, so everything else relaxes, then by the spectral theorem, the spectral gap, this integral exists. And this is a kind of generalized inverse of d. And so here it is. This is the generalized inverse relation. It's not the Moore-Penrose generalized inverse because there's not this isn't an orthogonal projection, but this is the relevant generalized inverse in which we can write everything. Okay, so this fact that the rho of t looks like some evolving thing just on the B space after a short initial time was proved by these physicists, Zanardos and Campos Venuti, in a very general setting, not even assuming CPT evolutions. We will work in the trace norm and take advantage of the fact that CPT P maps are contractive in the trace norm. And here's the first precise statement of this that we can get. This is a version of the result. So if you take the full evolution, so I'm starting from something that is on this slow manifold, the M, and I evolve it, and then I project afterwards. That projection is hardly doing anything. This is of order 1 over gamma. Okay? This is for all times. Now, if I wait a little bit, so the A is the spectral gap, if I wait a short time, then there's a constant C, so that the evolution starting from the initial state is closely tracking the evolution applied to the projected state. So notice the difference in these two things. Here, the P projector is after the evolution, and here the P projector is before the evolution, and you've got an extra logarithm here because this P is going to quickly take you down to the projected time. Okay, good. So that's some basic control on how it's when staying close to the manifold. Now, what about the evolution? And what these people proved was that this R of t satisfies this equation. This is a coherent evolution. This is a minus I times the commutator with this HP, which is the so-called projected Hamiltonian. It's a self-adjoint reduced operator of the H. And so you've got this coherent evolution of times up to order gamma. So the coherent evolution equation you get by throwing away this term, okay, this can't describe what's going on for a long time, which is what we're interested in, because, well, at times of order gamma, the errors add up to something of order 1. But more important, we know there's dissipation in our system, and you never see that with this coherent equation. So what goes next? Okay? Yeah.
Could you remind, so what is gamma again?
This gamma. Yeah, so this okay, so this, oh, whoops, which slide am I on? Let me see. Go on. So the gamma, yeah, let's.
Coefficient of the dimension
That means
I've gone way too far.
Gamma goes to
Here it is, right. It's this, so the gamma is this, so maybe a good thing, I should say, there's a close analogy here between what goes on with the Boltzmann equation. The Boltzmann equation, you have a coherent streaming part for the molecules, and then there's the collision mechanism going on. The collision mechanism has a parameter in it. Both kinetic theory people do 1 over epsilon, but gives you a large parameter. So this is the Knudsen number, so-called. But then there's a separation of scales. So what's happening is the time scale on which things change due to molecular collisions is very small compared to how the streaming acts. And so this term is big. So we should think of this as a separation of scales phenomena. the scale, the time scale on which the dissipator acts, the heat bath acts coupled to the boundary is very short compared to the coherent time scale. And so gamma is the ratio of these two time scales. Okay? So we're looking at things in the limit where the heat bath is acting much, much, much faster than the coherent evolution. That's the Zeno limit.
Yeah, just trying to clarify, so you mentioned that D doesn't have to be symmetric, right? So that D
Right.
may also have coherent terms in your setup.
Excuse me?
D may also have coherence terms in your setup.
It can, right. And those would get multiplied, but right, so the general dissipator, this is just the general dissipator. So, you know, it won't, I mean, if you get it from the Davies mechanism, it will necessarily be something that satisfies detailed balance and be then symmetric in the GNS inner product and be diagonalizable. But if you get things more generally a la Kosakowski from a singular coupling limit, then anything is possible, and then it can have its own Lamb shift Hamiltonian built in. But that would be a Hamiltonian acting just on the HA part, whereas this Hamiltonian that goes into K is the system Hamiltonian on the whole space. Okay, great. So good. So we're looking at things in this, it's a separation of scales phenomena, just as you have when you're trying to derive hydrodynamic equations from the Boltzmann equation. Okay, that's sort of really the analog of what we're doing here. Okay, good. So now what happens if you go on to longer time scales? And this was looked at by Popkov, Essink, Priscilla, and Schutz, and various combinations of these authors have written several papers on it, and they derive the next order equation. And next order, here's this term that we had before, and here's, now notice the gamma comes out in the inverse. Okay, so the dissipation is small, as you'd expect, because it's coherent up to times of order gamma, but then if you wait really a long time, you begin to see the effects of the dissipation, and there is this funny looking combination here. I'm missing a parenthesis. So you apply K, you apply this generalized inverse, and you apply K again. That looks a little quadratic, which is good, maybe like a second derivative, because this K is a commutator. And what these guys proved is that, I mean, it's evident that this KP generates a CPT evolution. It generates a unitary conjugation. The Priscilla, Essink, Popkov, and Schultz proved that this DP is a Lindblad generator under certain conditions, most of which is a positivity condition. So this is also a Lindblad equation, and hence generates a CPT evolution. Okay? Now, the proof that you can write this thing in Lindblad form, including with its own Lamb shift Hamiltonian, is non-trivial. But you can sort of imagine how it goes. You can see that there's this K in this thing. Here's the theorem coming up. This K is quadratic, so you do an expansion in breaking up the Hamiltonian into various pieces, and then you've got some matrix shows up at some point, and you have to diagonalize it. And if it's got all positive eigenvalues, you can write things in the Lindblad form, and if it doesn't, it doesn't. So you need some matrix to be positive. Yes?
Sorry, what is the Lamb shift in the context of Lindblad generators?
Excuse me?
What is a Lamb shift in Lindblad generators?
Where do I have this guy? I'm going backwards. Okay, it's this guy. When you run, okay, when you, if you're familiar with, I mean, in the Davies proof, if you take your system Hamiltonian, and what the Davies did, he looked at the evolution coupled to the heat path in the interaction mode. You take the weak coupling limit and so forth. And what you get are these jump operators. And you also get something that's called, in analogy with what goes on in electrodynamics, the Lamb shift Hamiltonian. So the general Lindbladian has this form. And these are this is the jump operator part. And this is the so-called Lamb shift part. And if you've got a specific model for deriving the Lindbladian, either from weak coupling or from what seems to be less familiar, but the singular coupling limit of Kosakowski, then you get all of these terms. Okay? So now if you do the second order expansion that I'm describing here, right, then you indeed get from this guy, if you expand it out, it in general has a Lamb shift term in it. Okay, so just like if you do the Davies method, in general you get a Lamb shift term. Okay? Now, the thing that enables you to write this in the Lindblad form and compute the jump operators is this inequality here, which is a general inequality for generators of CPT semigroups that we devised for this purpose. We're not assuming anything is self-adjoint here, so, but this follows from an inequality of Lieb and Ruszkai, and using this, the matrix that shows up in the analysis of Schutz, Popkov, Essink, and Priscilla can be diagonalized, and you get, indeed, this form, okay? This matrix, this inner product which shows up in here is the inner product with respect to the so-called G and S norm. And that's just, this just comes up naturally in the analysis. So just making, so in any case, the work of these guys, PEPS, they realized that you would get a Lindblad form out of this. This is not obvious. We computed the equation to next order. If you look at the next order equation, it doesn't generate a CPT evolution. And this is related to the fact in kinetic theory, if you try to go beyond the Navier-Stokes equations, you get something called the Burnett equations, which have very bad behavior, okay? You're approximating a completely positive trace-preserving evolution, but when you truncate, it's not guaranteed that at any order of truncation, you get something which is CPTP. It's kind of, it's nice that you do it second order, okay? And so we've proved this now, building on their work in complete generality. So this always happens just under our assumptions. Okay, good. So what's the precise statement of this thing? So here's the theorem that we've proved. So we're assuming, again, just a spectral gap and the ergodicity. And then if you look at this R of t, and here's where it's defined, down here, okay, then the R of t evolves under this reduced, this is the projected Lindbladian, which has the 1 over gamma in it, and this gives you an accurate description out to times that are of order t squared. So when t gets, gamma squared. When t gets to gamma squared, then you're up to order 1, you've lost information, but as long as t is small compared to gamma squared, then you've got good control over the evolution that's described by this thing.
Is that also true in the CD norm, or?
Well, let me see, what do you mean? So this is...
So it doesn't depend on the systems on the auxiliary.
Well, no, I don't, so no claim about that. But this is in, this is just on, where am I doing it? Okay, this is just in the one norm on the B space. So what was important for deriving this result was I was able to transfer the rate of decay from the A system to the AB system, okay, without knowing that this is the size of the B. So we use that there, but then this is just the bound on the B system. So we don't need to, there's not a third equation in it. Okay, so that's that. Now, we're interested in stationary states. This gives us control up to times of order gamma squared. We'd like to go further, and we would like to be able to treat general initial data, not just initial data, which is starting on the slow manifold. But this can be nicely done using the things that we have over here. So here I take a general initial data, rho naught on the HAB space. I run it forward under the full evolution, okay? And now I'm looking at what happens if I take pi a, tensor that, and do this reduced projected Lindbladian evolving just the B part, where the R naught is the partial trace of the rho naught. Okay? And then you do Minkowski's inequality, and you add and subtract a bunch of terms. The last theorem applies exactly, this guy's small because of the last theorem, and these two guys are small because of the first theorem that we had up there earlier. So what this gives us is this kind of bound over here, and right. Okay, and so this gives this precise statement that this justifies this reduced Lindbladian of Priscilla, Popkov, Essink, and Schutz in precise terms. So in complete generality, it really is telling you how this R is evolving. Okay? Good. Okay. And so let's just say a little bit about, where this thing comes from. If you take any density matrix on HB, okay, then you let R of t be the thing you get by tensoring on pi of a, so you're up in the full space, then revolving that forward. And then we use the Duhamel's formula, okay, to relate these things, and the fact that if you apply e to the t gamma d in this is in the null space of D, so that doesn't do anything, right? And so now you can relate R of T to this, and now you can iterate. This is the starting point of like a Dyson expansion, if you wanted to put it in physical terms. And what we'll take use of is we don't know much about this term over here, but see, since this is CPTP, and this is a density matrix, this term has norm 1, and so if you control things in the iteration, you can get very precise control of that. But they were making essential use of the fact that this thing, whatever it is, generates a CPT evolution, okay? And so then this proves this theorem that we had here. Okay, we see I'm going back, yeah, good. Going backwards, okay. And then, right, so this was starting, right, okay, so, sorry, I'm running back. I'm just getting confused with this thing. Okay. Right. Okay. So this, the theorem which we just had up was for the special states, but then we do this Minkowski inequality and the first two theorems, and now we've got a theorem which applies to general initial data, but you have to wait a little bit of time. And notice the way this is worded now, the time interval in which this bound is valid, you have to wait for the initial layer to take place, and the t. You can go out to gamma of t, because instead of having a gamma squared downstairs, I'm letting this guy be as large as gamma, okay? It's just a convenient way to write this thing, okay? So in particular, if you take gamma going to infinity, this evolution of this thing converges to this, okay? So as gamma goes to infinity, the full evolution converges to just applying this evolution for the projected Lindbladian on the slow manifold. And since for large gamma, this projected Lindbladian doesn't differ much from the purely coherent thing, if you take when you take the Zeno limit, the evolution looks just like this coherent evolution after the initial projection. So in the Zeno limit, all of the dissipation takes place instantaneously during the initial passage from rho naught to pi a tensor r naught, and from then on the evolution is coherent. Okay, so in the Zeno limit, the stuff is kind of trivial, but what we're interested here is understanding the situation near the Zeno limit and not actually at the Zeno limit, and then there's more to say, okay? And to do this, we need to introduce a third Lindbladian into the game, okay? So far, we've been talking about this Lindbladian, the projected Lindbladian here, this LP of gamma. This is the Lindbladian introduced by Priscilla, Popkov, Essink, and Schutz. And but the L gamma is what we started from. And we showed that it was a Lindbladian generator, and there's some more generality, but it's the formula that they had. Now, if you want to look at really long-time behavior, you can't do so much with this. It's hard to analyze, partly because both of these guys have two different time scales in them. The dissipation is really fast in this guy, and it's slow in this guy. This has a gamma in it, the other one has a gamma inverse. And these are hard Lindbladians, therefore, to estimate mixing times for directly. And what we would like to do is to get an equation that doesn't have a gamma in it. And again, one should think in terms of Boltzmann equation or kinetic theory. When you start from the Boltzmann equation, there's this large parameter, which is the inverse Knudsen number. You take that off to infinity, that pins you to the manifold of Maxwellians. The hydrodynamic equations tell you how the moments evolve, the hydrodynamic moments, but the Knudsen number does not appear in the Navier-Stokes equations, right? So what you have to do is the scaling. So you make another transformation, and you get rid of, you make a time transformation and a spatial scaling, and you eliminate the Knudsen number, and you get a new evolution equation which is independent of the gamma. That's what we would like to do here, and time scaling is something you can do, but you need a substitute for the spatial scaling. Okay.
Can I ask a high-level question?
See, yes.
Because you have shown that the two L gamma and LP gamma, they're related to each other, well, up to some time. In which sense? You can talk about the relations between the stationary states of the two?
Yeah, that's the goal. That's what we would like to do. And what we're going to go through is this third thing. So I'm going to give a precise relation between the mixing time for these two things and the third thing.
So
okay?
So the very fact that you can talk about the two means that for the bound you had before, the time is already long enough to pretty much allow you to approach this.
Right. I mean, it's suggestive of that. And of course, for the first bound, you know that you've got the coherent evolution is accurate up to times of order gamma. Now, as gamma goes to infinity, that means the coherent evolution is more and more accurate. But it can't be the right answer for the time goes to infinity limit because you've got some ergodic process in the end and you've got to converge to something stationary. Now, at the second order, you've got something a little better. You have a description in terms of the projected Lindbladian, which is accurate out to times of order gamma squared. As gamma goes to infinity, that's getting better and better, but you don't really know that it doesn't suffer from the same disease at this stage. Okay, but that turns out to be correct. I mean, this guy does give you the right thing. And to prove that, we're going to introduce a new Lindblad generator, and it's derived from these two pieces using exactly the method that Davies used in his derivation of Lindblad evolution equations and the weak coupling limit. So we've seen these formulas showing up in several talks already. Let me remind you, for any superoperator T, define this thing. So you take your X, the operator, you run it forward under the coherent evolution, you apply T, run it backwards under the coherent evolution, and average integrating from minus T to T. Okay? And it's easy to see that this limit always exists. The convergence can be estimated in terms of spectral properties of HP. It depends on the gaps between the Bohr frequencies, but okay, that's what it is. So this is something Davies introduced. Okay, so what we're going to do is we're going to do again what Davies did. You take your R naught and you run it forward under the projected Lindbladian, and then you run it backwards under the coherent evolution, and then we want to let gamma go to infinity and see what we can say about that. Now, Kp and the projected evolution differ by a term of order gamma inverse. So you would expect this thing to differ significantly from the identity only of times of order gamma. So let's introduce rescaled time, so T equals gamma tau, and we will then show that if you take the gamma goes to infinity of this thing, so you take now gamma times tau of the projected Lindbladian, run it backwards under the coherent evolution, that converges to this thing, which is the dp with this sharp operation. So the dp was the dissipator we had before, okay? And the sharp operation is this sharp operation that we had up.
One quick question, but is the sharp operator independent of gamma?
The sharp operator is independent. Let me go back to it. Yeah, I mean, here it is, right. It's independent of gamma because this operation is defined only in terms of the coherent evolution. Okay, so what's happening is the coherent evolution is happening really, really fast in this limit after you rescaled it, and so you're doing oscillations over the averaging, and so that's how that's defined. Okay, good. Okay. So, good, okay. Yes, okay, so there's the D, and so one can compute this dp sharp. Okay, so it's the dissipative part of the projected Lindbladian, and that comes out in this thing, and then you apply this sharp operation to it, and this is the theorem. So this is where the semigroup comes from. So this does not directly refer to the evolution governed by the L gamma, right? This is just relating the projected evolution, okay, and this new thing. But we already have results that relate the full evolution to the projected evolution. And so putting these two things together, one can get this statement over here, which is maybe the best way to think about it. So what you do, take something that's on this slow manifold, pi A tensor any density matrix on B, run it forward for time gamma tau under the full evolution, trace out A, and then run it backwards under the projected coherent evolution. That's the same thing in the gamma limit, in the Zeno limit, as running it forward under this new Lindbladian. Okay? And now this is something that we can use. So there's no gamma in this thing. This is something we can use to control mixing times and relate the mixing times of all these things. Okay? So the total variation distance is this thing. It showed up in several talks already. The 1/2 is traditional for probabilists. It means that this total variation distance between any two density matrices is less than 1 with equality if and only if the rho 0 and rho 1 are on orthogonal subspaces. Now this will be slightly different in the mixing time here. So we want to test for whether things are ergodic or not. So I don't want to refer to a putative invariant state. So this is another way it shows up in the classical literature sometimes. The mixing time is this. You take an epsilon between 0 and 1/2. You look at the first time the total variation distance between any two starting points gets to be less than epsilon. And then you take the worst case. You take the sup over all rho and rho 0. Okay, this doesn't refer to any steady state, and there may not even be one at this level. Okay, so the convention is that this T mix L epsilon is infinity if there is no such time. Okay, so it is known that if the mixing time here is finite for some epsilon, then it's true for all such epsilon, and then there will be a unique steady state, and then there's up to a factor of 2 difference from the usual T mix where you put the steady state in from the beginning, right over here. But what we would like to do, well, let's say what we'd like to do. So here's the theorem. So for all but at most countably many values of epsilon 0, the mixing times are related by this. Okay? So this doesn't have a gamma in it. So if you can compute the mixing time of that and find out that it's finite, then these times, of course, live on a different time scale, right? So you'd expect this gamma to be down here. But this T mix of this thing divided by gamma is close to that. Okay? This is all, I mean, every theorem about limits is a theorem about lim imps and lim sups. And of course, this function, this mixing time function is a monotone function, and monotone functions can have only countably many jumps. And what you've got to do is avoid this jump discontinuities if there are any, probably not of this thing. If there are no jump discontinuities in this guy, then it's for every epsilon. But I mean, that doesn't really matter for us. So consequently, if this guy is gapped and ergodic, so the mixing time is finite, then these guys are gapped and ergodic, which is useful because you can't, I mean, you don't have to, this is this complicated Lindbladian with a dissipative part and a coherent part acting on different time scales. But if you know that this guy has a finite mixing time, then this guy for large gamma has almost the same mixing time, and so is this. Okay? There's another way in which this dp sharp governs the long time behavior. And suppose that dp sharp is gapped and ergodic. Let R naught be its unique steady state density matrix. And then, okay, we know that there's a unique steady state for this equation for all large gamma because the mixing time is finite. And then the statement is that as gamma goes to infinity, the unique steady state for the full system is pi a tensor R bar. Okay, so what we would like to do now is, wrap this up, we would like to apply this to the computation of non-equilibrium steady states. Okay, and there's a large literature on doing this perturbatively and finding currents in the non-equilibrium steady states and so forth. The simplest approach, many cases are of this type, one considers a Lindblad equation like this. So there's an L0 plus epsilon L1, and L0 is ergodic, and it has a unique density matrix, steady state density matrix, rho bar naught. Okay, so what one does, this is throughout the physics literature, you assume that there's a unique density matrix for the perturbed problem and that it has a series expansion in epsilon. Okay, you plug this series expansion into the equations and you equate like powers of epsilon and you get an infinite hierarchy of equations. Okay, now can you solve these things? Well, when the L0 is ergodic, its range consists of all traceless operators. And if L1 is also a Lindblad generator, everything in its range is traceless, so the Fredholm alternative is trivial, and these equations are all solvable, and you can do it, okay? And if you can then control the size of the terms, you can make sense of this. Okay, now our problem is of a different sort, because in our problem, the D plays the role of the L naught, and it's far from ergodic. It's got a huge null space, and what do you take as your starting point for the expansion? And indeed, this problem comes up in the physics literature. There are papers of Prosen and so forth, and what people have done in specific cases is solve the thing in a spin chain problem for 4, 6, and 8 spins and guess, based on the direct computation, what the starting point should be, and then carry out the calculation. However, in this setting, we get an actual equation for what the starting point should be, involving the new Lindbladian, and here's what it is, okay? Because this limit of the rho gamma, the thing we'd like to expand, in gamma goes to infinity, is pi a tensor r bar, where r bar satisfies the steady state equation for our new Lindbladian. That's the equation for the starting point, okay? So you take this as the starting point, and then you look for an expansion of this type, and you do the same thing. You plug this into the equations, and now these are the equations that you have to solve. And now it's a little more subtle, because the D has a large null space, and therefore it has a correspondingly small range, and you've got to satisfy the Fredholm conditions, and does this work out? Okay, and so there's a bunch of beautiful linear algebra. You can find the papers on the archive, so if you want to see how it goes, you can do it, but you can check the Fredholm conditions term by term, and they are all expressed in terms of the LP gamma and the KP. Okay, everything lives on B. So these are equations in the full space, but you can reduce them to equations just on the HB. Okay, we'll explain that, but there's a nice reduction, and the upshot of it is then when this dp sharp guy is ergodic and gapped, then all of the equations are consistent. You can solve them all, and you can control the growth of these conditions, and you get what you'd expect, an exponential growth. So if the gamma is bigger than this C1, because the gamma is going to be downstairs in the thing, then you have a geometrically convergent expansion, and you can even estimate the errors on the remainder. And so here's what comes out of this. So under the assumption that dp sharp is ergodic, there's a uniquely determined sequence solving the system of equations. We've got some bounds like so, in terms of these norms, all of which can be estimated, okay? And so if this, okay, so consequently for gamma bigger than this constant, this right over here, this constant, then we get convergence in the trace norm, and this is your unique steady state, okay? So let's look at a simple example. There's a follow-up paper we're doing, which is a fermionic spin chain example with the HB having arbitrarily many sites, but that gets a little complicated. Let's look at just the simplest example and see how you compute these things, just to wrap things up. So let's take HA and HB to both be C2 with the usual inner product. We'll write things in terms of the poly matrices, the sigma plus and minus, and let me look at this Lindbladian, which has the jump operators, which are linear, the jump operators here are the raising and lowering operators, okay, on the first site. And I'm putting in a temperature beta, and this is a familiar example for many people. I keep going backwards with this thing. This is the thing which has the Gibbs. The steady state for this thing is e to the minus beta sigma 3 normalized, okay? And you can do some simple calculations of the eigenvectors and eigenvalues, and so it is ergodic with a spectral gap of 1, and now you can compute stuff. Now let me just say a little bit about this. If you want to compute this projected Hamiltonian and the projected generator, what you do is you take the eigenbasis of the dA, you compute its dual basis. This is the thing, so if you take the inner product of this with any one of these, you get 1 if the indices are the same and 0 otherwise, right? Okay, so you can expand the H in terms of the first factor being each in this dual basis, call these guys the G's, and from that you can easily work out what the projected Hamiltonian is, okay? And what this dP is the dissipation for the on the B space. And it turns out in this example that the dP has the exact same form as dA. So in fact, the dP also satisfies the detailed balance condition with respect to this. Okay? So then simple computations show that if the HB equals 0, or HB commutes with sigma 3, HB is the Hamiltonian in space B, then the steady state is just exactly pi a tensor pi a. Okay? Now, something more interesting happens if you take an HB which doesn't commute. So if you take the HP to be, so you skipped a page, yeah. Okay, good. Oh, no, okay. So what we're going to, okay, yeah. So yeah, okay, and then you can compute everything with that one. So let me skip to the more interesting case here. Let's consider the case in which HB is equal to sigma 2. Okay? Now the steady state for the full system is no longer the tensor product of pi a times pi a, and you can compute what it is because we've got a 2-qubit system. So you put it into your, I use Maple, you use whatever you want to do, and you can just compute everything in sight. And so here is what the rho gamma. So the leading term is this, as you would expect. Here's the gamma inverse stuff, and here's gamma to the minus 2, et cetera, et cetera. So this is just direct computation for the full model. And in particular, you can get the partial traces of these states. This is the you trace out B, so this is the reduced density matrix on A, and this is the other one, the leading order. And you can compute the spectrum of this thing. And so the eigenvalues are indeed -1, and for the real parts, -3/2 over gamma. You can find the steady states and everything, and so that's what that is. Now, you can compute the dP sharp, and so here's what the dP sharp is. In the paper, you find formulas, and so this is just to show you, since you don't have the formulas that we're using the theorem from, you can't go from here to here, but I just want to show you that you can write everything out fairly explicitly if you have the formulas, and this is the exact form of this Davies projected oscillation averaged Lindbladian starting from this dP that we computed. This is what the sharp of it is. So it turns the jump operators, which were built out of the sigma 1, sigma 2s, into these guys, which is the sigma 1, sigma 3s, and that's the Lindblad, that's the dP sharp. And again, the eigenvalues are -1 and -3/2, just as you would expect from the other theorem, because this is what, so the spectrum is matching up just as you would expect it would from our claim that the mixing times are matching up. Okay, and so that's that. And then you can use this to compute the steady state. And I'll wrap this thing up here because we're right about to go. So don't try to read all the calculations, but if you take this steady state here and apply K to it, you get, everything's written in terms of Pauli matrices, so you can compute it. And you now have to solve this. So the equation for the N naught is that D of N naught is equal to this. Okay? So this is indeed, has the trace, satisfies the right trace condition. So the general solution is going to be the generalized inverse, which just puts in a minus sign on these things, plus the general thing in the kernel. And then you have to figure out what that is. And the way that works out is this is going to show up in the compatibility conditions for the next 2 stages. So you first get the part of X, which is some traceless self-adjoint matrix that's in the image of, that's in the range of KP, and then the part that's in the kernel. Okay, and so checking the Fredholm conditions, that tells you in 2 stages what the X is, and lo and behold, you do the calculations, and here's exactly what N naught is. And so the N naught coming from these equations is consistent with what we found by exact calculation before. Okay, and so this is how it goes. Okay, so thank you very much for your attention.